continue with some more problems. All right, in the equation Ni is, do you know which element? Nickel. Cu? Copper. And then nitrogen and oxygen combined in this ratio is called nitrate. And so this is a compound called copper 2 nitrate. This one is nickel nitrate and nickel 2 nitrate. This is copper. So nickel metal, copper 2 nitrate. This is a chemical equation in which this arrow represents produces or forms or yields. It produces nickel 2 nitrate and copper metal. Which of the reactants is our elements? So the stuff on the left are the reactants, the stuff on the right are the products. The reactants react to form products. Which of the reactants is our elements? Nickel, this is a compound. And which of the products is our compounds? Copper would be an element, this would be a compound. And then we're good. Okay, when the Romans were developing calcium carbonate, they had to add something to this. What did they have to add to the calcium carbonate? Heat or energy. And so energy being added is called endothermic. And so if we have to input energy into making this go, we call it endothermic. And the energy is going to be consumed as what we call a reactant in this case. And so this is endothermic. If energy is produced, we call it exothermic. And so endothermic, exothermic. Energy being inputted, endothermic, energy being taken out, exothermic, or produced, exothermic. And so which of the following processes is our exothermic? Water freezing. And so there are different ways we can visualize water freezing. One way of visualizing water freezing is like this. We not only do we write chemical reactions in forms of chemical equations like this, but we also do physical processes. Yes, that's an equation as well. And so if we're looking at water freezing, let's see if I have one more pen. Then we're going from H2O, what? If we're looking at water freezing, we're going from H2O liquid to H2O solid. Okay, so what do I have to do? Do I add energy to H2O liquid? That is, would I heat up water to get it to freeze? No, I have to remove it. And so I have to remove energy from the water. And so what I'd be left with is ice, and I got to get rid of that energy. Well, how do I get rid of the energy? I dump it behind the freezer. You know, the freezer is going to get hot in the back there, and so it gives the extra energy, right? And so this is exothermic here. And so freezing ice, or it's not freezing ice, freezing water is exothermic. But the opposite, what's the opposite process? Melting. Melting, do I add energy to ice to melt it? Yes. So melting would be endothermic. And so if I go left to right here, it's exothermic. If I go right to left, it's endothermic. And there's something called conservation of energy, just like there is conservation of matter. And so it's the exact same amount of energy. Whatever energy I had to remove to freeze it is the exact same amount of energy I have to input to melt it. It's conservation of energy. It's called energy is neither created nor destroyed. It also has another name, which is the first law of thermodynamics, but you don't have to get there just yet. It's just energy is neither created nor destroyed. It's conservation of energy. Okay, water vapor in the air changing to liquid water droplets on a window pane. And so what's happening there? Well, gaseous water is condensing into liquid water. And so in order to go from gaseous water to liquid water, do we remove energy or do we input energy? We got to remove energy. So this is going to be exothermic or endothermic? Exothermic. C, molten iron solidifying. Exothermic, too. D, chocolate candy melting. Endothermic. Okay, as a child plays on a swing, at what point in her movement is her kinetic energy the greatest? At what point is potential energy at its maximum or at its greatest? Yeah, so if you've had physics, then you know. You know, in physics, we know something. What we know from physics is this. We know about kinetic energy. Kinetic energy is the energy of motion, but there's also potential energy. Potential energy as well. And if we look at kinetic energy and potential energy and we combine that, then we get the total energy. So normally when we think about kinetic energy, we think about hot objects or cold objects, this kind of thing. We think about the temperature, right? We don't always think in terms of potential energy. And so here I have this three-hole punch. This three-hole punch is at room temperature. You know, this three-hole punch, you know, well, maybe I'm just going to put it up on the ceiling there and just kind of hang it with some Scotch tape. Is that a good idea? No, because eventually it could fall down. But you think about that. If you think about having this up here, what's the difference? Because it's still at room temperature. And so the kinetic energy is the same. You know, it didn't get hotter. Is it hotter up here? No. And so I know that hot objects have high energy. You know, hot objects, high energy, cold objects, low energy. And so when I think about this being way up here, it's no hotter, it's no colder. The kinetic energy is exactly the same. So what's the difference? I don't want to put this on the ceiling because it could fall and hit me in the head because it has high potential energy. And so this is the same thing with you know, in physics. We have the same thing in chemistry. Let's look at physics, for example. In physics here, if somebody's on the swing, you know, they're either at this extreme or this extreme, but they're going to pass through the center here. And so where will they be moving the fastest? Where's the highest degree of motion?
At the center.
At the center here. And so here we're going to have max kinetic energy. In fact, we should have the lowest, this is gravitational potential energy, right? Because this is the lowest point, and so they can't fall any farther down than this. And so the potential energy is at its lowest here. And so this is max kinetic energy. Whereas when they're at the top of the swing or at the end of the swing here, are they moving very fast? No, in fact, they come to a stop. They got to come to a complete stop in the reverse direction. And so here the kinetic energy goes to zero, and we're at max potential energy. They're the highest up here. They have the greatest distance to fall. And so chemistry works in exactly the same way. What has a higher energy? You know, I'm going to say a jug of water. It's filled with hot water versus, let's say, a cold stick of dynamite. This is a cold stick of dynamite.
So what you said, kinetic or potential?
Well, okay, kinetic energy. The hot water. The hot water is dangerous because you could burn yourself. If you put maybe it depends on how cold. Let's say it's not that cold. It's close to room temperature. And you put a cold stick of dynamite, yeah, it's going to be cold to the touch. The hot water is going to be at higher energy, right? And so what would you rather transport in your back seat? A jug of hot water or a cold stick of dynamite? Cold stick of dynamite? Well, it depends because this is it. It's like this. today we're doing combustion of methane. So we have methane, which is a gas, oxygen is a gas. This is going to form some carbon dioxide, which is gas, and water. And the two water molecules. The water is going to be liquid. Let's say we start off in methane and oxygen. This is going to be at 25 degrees C. 25 degrees C is our standard room temperature. And so here I have methane. Let's see, can you hear it? Do you hear that? It's methane. You probably, it's probably hard to hear, but you probably can smell it pretty soon. Do you smell it? Yeah, you can smell. You can smell gas leak. Is that the smell of methane? No. Yeah, it's an additive. Methane has no smell. And so we want to be able to detect the leaks. So methane's not pure. In fact, this is natural gas. Natural gas has methane, ethane, an odorant, some other stuff. So it's a mixture. We can buy pure methane. That's no problem. Then we got oxygen. This is at 25 degrees C. And then we burn it. When I burn it, it's going to get hot, but eventually I'll let the CO2 and the water cool down, and then eventually it'll cool back down to room temperature. And so if I look at the methane and the oxygen versus the CO2 and the water, they look to be at the same energy, the same kinetic energy, because they have the same temperature. And so they're both moving similarly. And so are these at the same temperature? What would you rather fill your trunk with? Methane and oxygen, or CO2 and water? CO2 and water. Why is that?
They're less dangerous, less reactive.
Less dangerous, less reactive, less... Okay. And when you're saying less dangerous, less reactive, more stable, you're talking about potential energy. You're not talking about kinetic energy, because the kinetic energy of these two are exactly the same. The difference is potential energy. This has the potential to explode, whereas CO2 and water, like if you exhale on water and you light a match, are you going to worry? No. And so this is lower chemical potential energy. This is higher chemical potential energy. So in terms of gravity, then the CO2 and the water are down low like this, whereas the methane and the oxygen are like having a brick, hanging over your head. This is high potential energy, even though the kinetic energy is the same. And so this is at the top of the swing. This can fall down to the bottom of the swing, and that process is going to release a lot of energy. And for me, I'd rather have hot water than a cold stick of dynamite, because a cold stick of dynamite has a huge amount of potential energy. And so this is much more dangerous than this. And so I'd rather risk a burn with hot water. Well, it's the same thing in physics and chemistry. So let's take a look here. The next example. Actually, there are no more examples of potential and kinetic energy. But after solid limestone is heated, the rock that remains weighs less than the original limestone. What do you conclude happened? Is that a violation of the conservation of mass? Yeah. What happened was the carbon and oxygen left the CO2, and the CO2 gas escaped. And if we could capture it and weigh it, we could actually see that the weight didn't really change, the mass really didn't change. Okay, we'll continue on here. The photograph below shows a beaker of water. These are beakers here, with this cup, and a sugar cube. So this is a sugar cube. Is that one single crystal? No, that's a whole bunch of tiny crystals put together in a cube shape like that. It might be a single crystal. If this were a single crystal of sugar, it would be as transparent as that. Okay. The sugar cube is then placed in the water and it dissolves completely. So if you take this sugar cube, put it in water, it dissolves completely. Do weights need to be added or taken away from the right pan to make the system balance. So if we take this sugar cube, dissolve it in water, do we have to add or remove weights here? No. It'll still be balanced because we aren't. Now, if the sugar cube dropped off the pan, yeah, but sugar cube, it's just going to be dissolved in water. Now the liquid in here is going to weigh more. It's going to be the water plus whatever the sugar cube weighed. That's what it's going to be. So atoms are neither created nor destroyed in that case. '63. Identify several energy conversions that occur regularly in your home. State whether each is useful, wasteful, or sometimes useful and sometimes wasteful. This talks about converting energies. So, for example, converting electric energy into heat, or converting electric energy into motion, like a rotational motion, or converting heat into other things. So we'll talk more about that when we dig into energy deeper. So I'm going to skip that question for now. Determine whether each of the following statements is true or false. The fact that paper burns is a physical property. False. Particles of matter are moving in gases and liquids, but not in solids. It's false. A heterogeneous substance has a uniform appearance throughout. False. Compounds are impure substances.
No,
That's
that's false.
false.
You have a bunch of the same compounds.
Hey, water is a compound. Is water an impure substance?
Is the pure substance.
Water is pure. Yeah, compounds are pure substances. If one sample of sulfur dioxide is 50% sulfur and 50% oxygen, then all samples of sulfur dioxide are 50% sulfur and 50% oxygen.
False.
True. True. That's true because compounds have fixed composition. Mixtures have variable composition. This is like saying if sugar water is 50% sugar, 50% water, then all sugar water is 50% sugar and 50% water. True or false? That's false because you could have all kinds of sugar waters, you know.
So if you
However-
stating compound, does that technically still mean that that's the way we would read that question? Because there's no word saying compound.
No, sulfur dioxide, no, actually, you're right. Sulfur dioxide is a compound. It's not a mixture. Yeah, they could say a mixture of sulfur and oxygen. If you're talking about a mixture of sulfur and oxygen, then it could be any. Or if you're talking about a mixture of hydrogen and oxygen, it could be many. But if you're talking about water, you know what they call water? Dihydrogen monoxide. Have you ever heard of it? Dihydrogen monoxide has a scary sound to it, right? Did you hear the story? True story? Some people wanted to play a joke on the city council of this town up north, Northern California. And so they convinced them to ban dihydrogen monoxide because it's toxic. You could die. It's potentially lethal. Of course, you could drown, right? And so they didn't say anything that was false, but they got the city to write a declaration banning dihydrogen monoxide. Anyway, if you see a name like this, it's probably a compound, versus they would have to say a mixture or something like that. F, a solution is a homogeneous mixture. Yeah, okay, that's the definition. Solutions, you could have three types of solutions. Gaseous solutions or gaseous mixtures are homogeneous, all of them. A solution, by definition, is homogeneous. It looks uniform. So liquid solution would be something like salt water or sugar water. It's homogeneous. And a solid solution would be an alloy. And so if you look at if you look at sterling silver, does it look homogeneous or heterogeneous? Homogeneous. If you look at 14 karat gold, which is a solution of gold and whatever else, heterogeneous or homogeneous? Homogeneous.
So all gaseous solutions are homogeneous?
All solutions are homogeneous. I didn't say that, but all solutions are homogeneous. F. G. Two positively charged objects attract each other. That's false. Two negatively charged objects repel each other. That's true. The first part is false, the second part is true, so the whole thing we're going to take is false. H. Mass is conserved in an endothermic chemical change, but not in an exothermic chemical change. False.
No, mass is always conserved.
Yeah. It depends on how detailed you want to get. You know, like I said, the changes in mass are so minuscule that we essentially think that mass is conserved. And so mass is conserved. Because the energy changes are kind of small. I. Potential energy can be related to positions in an electric field. Electric field, positions in electric field. Yeah, potential energy. Well, potential energy is not kinetic energy. So this, if you have an electric field, what did I say an electric field consists of? Positive. And then over here we have negative. Did I show the electrolysis, or did I run out of time?
You showed rushed at the end.
I rushed at the end? Okay. Well, this is how water becomes electrolyzed. You can form hydrogen and oxygen. If you put enough positive charge and enough negative charge on these, you can get water to decompose into hydrogen and oxygen. But it depends on your field. So if you have a negative particle, you know, the closer you bring it to the positive, the better. The closer you bring it to the negative, the worse. So it depends on the position in the electric field. Yes, it does. But this is more a physics question, I think, than a chemistry question. So I wouldn't ask a question like that. J, chemical energy can be converted to kinetic energy. Is that true or false?
True.
That's true. What happens when you burn methane? Yeah, when you burn methane, you generate a lot of heat. That heat is kinetic energy. Heat is the transfer of kinetic energy from a hot body to a cold body. And so that's what happens. Chemical energy is converted. And so this is the way that happens. What happens when you go down a slide? When you go down a slide, you're converting gravitational potential energy into kinetic energy. Here. And then you stop. If you didn't stop, well, how do you stop? You stop by generating heat. Friction, through friction. Convert that potential energy into kinetic energy. Potential energy is more powerful than kinetic energy. It's false, you know, because potential energy depends on what you're looking at, and kinetic energy also depends on how hot it is, you know. And so we don't know. Kinetic energy in the sun is huge, you know. That's enough to destroy all the molecules that are around. A chemical change always destroys something and always creates something. Well, in a way it's true, because, you know, is the methane still around? Methane's not around anymore. And what you can say is the atoms are rearranged, but if you want to be dramatic, you could say the methane was destroyed. The oxygen destroyed it, or something like that, and it was creating CO2 and water. And so this could be true. It depends, you know, on semantics. But were the atoms destroyed? The atoms weren't destroyed. And so it's tricky. 67, a natural food store advertises that no chemicals are present in any food sold in the store. If the ad is true, what do you expect to find in the store? Nothing. Well,
It's chemicals in the tube.
well,
The natural.
I don't know. I mean, do you call water a chemical or you don't call water a chemical?
It is
To a chemist, everything's a chemical, but for natural food, they should have said maybe artificial chemicals or, additives or that kind of stuff, Then it makes sense.
So else you ever take a joke question?
Yeah, it's a tricky question. It's just because the way chemists define, chemists define chemicals as the elements, compounds, and mixtures that comprise matter, and matter comprises the entire universe, and therefore everything's a chemical to a chemist. But again, it's semantics, so it's all right. Which of the following can be pure substances? Mercury, can it be pure?
Yes.
Milk? No. Water?
Yes.
Tree?
No.
Ink?
Yes.
Maybe. Iced tea? Ice?
Yes.
Carbon?
Yes.
Okay. Can you have a mixture of two elements as well as a compound of the same two elements?
No.
Yes. Yeah. For example, hydrogen and oxygen. You could mix hydrogen and oxygen gas together. That's a bad mixture
It's explosive.
because it's highly explosive. This could be at room temperature, so it doesn't have much kinetic energy. But if you heat this up, it's going to explode, for sure. And the compound would be water. And so mixture, you could have variable amounts of hydrogen, variable amounts of oxygen. Water, you can't. Water is fixed amount of hydrogen, fixed amount of oxygen. Can you have more than one compound made of the same two elements? If yes, try to give an example. More than one compound made of the same two elements. And the answer is yes. For example, carbon monoxide versus carbon dioxide. Same two elements, two different compounds. Have you ever heard of carbon trioxide?
No.
No, actually carbon trioxide doesn't exist. There's something called carbonate, but it's a bit different than carbon trioxide. Rainwater comes from the oceans. Is rainwater more pure or less pure, or the same purity as ocean water?
Purer.
Purer, more pure.
Distilled.
It's like distilled, right? Distilled water. Rainwater you can drink, unless it's black rainwater that is contaminated with soot or radioactive debris, etc. And so don't drink. 75. A large box contains a white powder of uniform appearance. One sample is taken from the top of the box and another is taken from the bottom. Analysis reveals that the percentage of oxygen in the sample from the top is 48.2%, whereas the sample from the bottom is 45.3%. Okay, answer each question independently. Is the powder an element or a compound? So at the top, it has a different composition than the bottom. Is the powder an element or a compound? I'd say neither. Or one.
It cannot be compound. If it was compounded, it would be more homogeneous. Wouldn't it?
All right, this is kind of a trick question. It cannot be an element. It cannot be an element because an element would be 100% the same thing, right? It can't. For example, this says 48.2% oxygen. Well, that means there's 51.8% something else. So it cannot be an element. An element would have to be 100% oxygen or 100% aluminum or 100% whatever. And so this cannot be an element. And then you think, can it be a compound? And you'd like to say no, because compounds should have a fixed composition, but it's got to be a compound. The only way this can be a compound is if this mixture, if this powder is a is a mixture. That's how it can be. And so what this could be is something like this. Let's say you have a container filled with iron filings. You know the symbol for iron? Fe. So if you have a whole bunch of solid iron powder here, what's going to happen is down here at the bottom, you're going to have iron, but here at the top, it's going to start to oxidize. Right? And so in this case, we could have a variation of the mixture. Up at the top, we have more oxide, iron oxide. Down at the bottom, we have less iron oxide. And that way, when you take a scoop of the powder, you would get more oxide in the top, less oxide in the bottom, and that's what explains that. B, are the contents of the box homogeneous or heterogeneous?
Hetero.
It seems to be hetero, but we can't tell, you know, yet, based on the information. Can you be certain that the contents of the box are pure substance or mixture? We can be sure it's a mixture. It's got to be a mixture, because if it's pure substance, the composition would change. Well, we're almost done with this. We might as well just finish the, let's see, how much time do we have? We go until 5?
Yeah.
I'm not talking too much. We got an hour. Well, anyway, we're so close to finishing this. I'll let you, though, finish it. How about that? Well, we'll take a look at a couple more. If energy cannot be created or destroyed, as the law of conservation of energy states, why are we so concerned about wasting our energy resources?
Because we're wasting the resources that create them.
Yeah, that's one of the things. We're wasting the. But we have different qualities of energy. Like electricity, you can do a lot with electricity. Electricity is like high quality energy, right? We also have low quality energy. Low quality energy you can't do much with. So with electricity you can run a TV, but let's say you have a whole bunch of heat. And so if I burn the methane and generate a whole bunch of heat, can I power my television with that? My computer? No. Is it easy to convert that heat that I just generated back into electricity? Well, I guess I could try to warm a pot of water, which generates a steam turbine and creates electricity, but is that very efficient? No. Versus something like hydroelectric, which is much more efficient. And so they're different. When we're talking about wasting electricity, sometimes energy is conserved, but sometimes it goes into the lowest form, which would be heat, versus a higher form. The highest form would be something like chemical potential energy. If we have chemical potential energy here, we have stored energy here we can use for different things. All right, but anyway, we'll continue with this later. Or actually, better yet, you guys continue with this. There's some advanced questions you should look at. But for right now, what I want to do is I want to talk about the lab. Okay, I don't think I need to record this.